Hello friends, in this video we are going to discuss about the circuit operation of 120-degree conduction mode 3-phase inverter for the interval number 4, interval number 5 and interval number 6. Okay, so here we have already discussed about the first 3 interval circuit operation, that is the phase voltage and line voltage waveforms, okay, in the last video. Next, let us move towards the fourth interval. During the fourth interval, switch number 3 and 4 will be in the on state. Oh, okay, so 3 is in the on state, 4 is also in the on state. Okay, so when 3 and 4 will be in the on state, if you check, yes, it is like switch number 2 will be in the open state. Okay, so phase A will be connected to the minus VDC, negative plate of the VDC, phase B to the positive plate of the VDC, and phase C is kept open. Okay, so it is like we'll be having, yes, phase A to the negative plate of the VDC, phase B to the positive plate of the VDC, and phase C it is a kept open. Okay, so if the phase C is open, so what about the VCN? VCN is equal to 0. VBN, if you check, is equal to VDC by 2, right? And what about the VAN? VAN is minus VDC by 2, minus VDC by 2. Okay, so if you check during the fourth interval, VAN is minus VDC by 2, right? It is a minus VDC by 2. Okay, so this is a minus VDC by 2, right? What about the VBN? VBN is plus VDC by 2, so it is a VDC by 2, same. And what about the VCN? VCN will be 0, right? VCN is equal to 0, so it is a 0, right? Next, this is during the fourth interval. During the fifth interval, switch number 4 and 5 will be in the on state. Okay, so switch number 4 and switch number 5 are in the on state, so switch number 3 is open. Okay, so switch number 4, 5 are in the on state. Okay, so let us short circuit the switch number 5. Okay, so if you check, phase A to the negative plate of the VDC, phase B is open, and phase C is connected to the positive plate of the VDC. Okay, so phase C to the positive plate of the VDC, phase A to the negative, and phase B is kept open. Okay, so from this, yes, we can write the phase voltages VAN, VBN and VCN. Okay, so if you check the circuit, we can write, yes, VBN is 0 because it is open, right? VBN is 0. What about the VCN? VCN is positive, it is a VDC by 2. What about the VAN? Yes, if you check, VAN, it is equal to minus VDC by 2, minus VDC by 2, right? So during the fifth interval, right, VAN is minus VDC by 2, right? What about the VBN? VBN is 0, so it is a 0, right? And the VCN is equal to plus VDC by 2, it is a plus VDC by 2. Okay, so this pulse is of VDC by 2 magnitude. Okay, and during the last interval, that is the interval number 6, switch number 5 and switch number 6 will be in the on state. Switch number 5 and switch number 6. Okay, so 4 will be the open circuit, 5 and 6 will be in the on state. Okay, so due to that, what will happen? Yes, so 5 and 6 are in the on state. Okay, 5 is in the on state, 6 is also in the on state. Okay, so if you check, phase A is open, so here it is a phase A, phase B, yes, to the negative plate of the VDC, and phase C to the positive plate of the VDC, right? So here, if you check the values of phase voltages, right, values of phase voltages, then we can write it as, yes, from the circuit, VAN, it is a 0, right? What about the VBN? VBN, it is a minus VDC by 2, right? Minus VDC by 2. And what about the VCN? VCN is equal to plus VDC by 2. It is a plus VDC by 2. Okay, so if you check, VAN is 0. VAN is 0. What about the VBN? Right, minus VDC by 2. And VCN, it is a plus VDC by 2. VCN is equal to plus VDC by 2. So these are the waveforms, right? This magnitude is plus VDC by 2. VDC by Okay, so these are the waveforms of phase voltages during the first six intervals. Okay, next, can we draw the line voltage waveforms? Yes, VAB. Okay, during the fourth interval VAB, if you check, it is a minus VDC by 2, minus VDC by 2. So it is a minus VAB. It is a minus VDC. Okay, it is equal to minus VDC, right? Next, during the fifth interval, minus VDC by 2 minus 0. So it is a minus VDC, right? It is simply the difference. Okay, and during the sixth interval, it is 0 minus of minus. Okay, VDC by 2. So it is a plus VDC by 2, right? So next, what about the VBC? VBC during the fourth interval. Okay, it is a VDC by 2 minus 0. So it is a VDC by 2, right? During the fifth interval, it is a 0 minus VDC by 2. So it is a minus VDC by 2, right? And during the last interval, it is a minus VDC by 2 minus VDC by 2. So it is a yes minus VDC. This is a minus VDC. Is this clear? Okay, so this magnitude is VDC. Okay, this magnitude is minus VDC by 2, right? It is actually minus VDC, right? So this is about the line voltages VAB, VBC. Similarly, we can draw for VCA as well. Okay, now if you check the nature of the phase voltage, yes, the nature of phase voltage, yes, phase voltage, yes, it is a quasi square wave, right? It is a quasi square wave, right? And what is the pulse width? Pulse width is equal to 120 degree. Pulse width is equal to what? 120 degree. Are you getting the point? Okay, so it is a quasi square wave and it is having a pulse width of 120 degree. This is the nature of phase voltage. Okay, so again, what about the line voltage nature? Line voltage is a stepped waveform. Okay, line voltage, it is a stepped wave, right? It is a stepped wave. Line voltage is a stepped wave, right? Next, so if you check the phase difference between phase voltages, okay, so whatever the waveform we are having, right, for VAN, right, that is a VDC by 2, VDC by 2, 0. It is starting in the VBN, VDC by 2, VDC by 2, 0. After two intervals, so can we write VBC is lagging to VN by angle 120 degree? Yes. Again, whatever the waveform we are having for the VBN, it is repeating in VCN, right? After, yes, negative 0, positive, positive. So it is a negative 0, positive, positive, right? So same waveform of VBN is repeating in VCN after two intervals. So VCN is lagging to VBN by angle 120 degree. Okay, so there exists a phase difference of 120 degree. Okay, next, what is the peak value of all the three line voltages? It is a VDC by 2, VDC by 2, VDC by 2. Okay, so peak values are same. Okay, so what about the frequencies? Yes, it is completing one cycle after 2 pi, after the sixth intervals, right? So frequency should be same. Okay, so here apart from the sinusoidal, right, all the requirements of the balanced three phase voltages we are getting and it is a fulfilled, it is a matched. Are you getting the point? There exists a phase displacement of 120 degree. Peak value of all the three phase voltages is same and they are having the same frequency as well. Next, if you check line voltages VAB and VBC, right, whatever the waveform we are having for VAB, the same is repeating in the VBC, right? After, yes, if you check, it is repeating after two intervals, VDC, VDC by 2, minus VDC by 2. So it is a VDC, VDC by 2, minus VDC by 2, right? So VBC is lagging to VAB by angle 120 degree. Similarly, you can check for VCA as well, right? What is the peak value of line voltages? It is a VDC, VDC. And again, after the 6 intervals, it is completing the one cycle, right? So that's why the frequency will be same. Okay, so apart from the sinusoidal, right, it is fulfilling all the requirements of the balanced line voltages as well. Okay, next, so here if you check, the phase voltage nature is quasi square wave with a pulse width of 120 degree. Line voltage is a stepped wave. Okay, so can we say that, yes, can we say that the line voltage, yes, it is like a 120 degree pulse width, right? So therefore line voltage In line voltage, which harmonics are absent? It is a all even and third harmonic are absent. All even and third harmonic are absent. Whereas, yes, the phase, sorry, this is actually in the phase voltage, not in the line voltage. Actually, this is in the phase voltage, right? Because the phase voltage is a Cauchy square wave. Okay, phase voltage is a Cauchy square wave. So it is a phase. It should be phase. Okay. Next, line voltage. If you check the line voltage, in the line voltage, yes, the nature is, it is a stepped waveform. Okay, so it is having the nature same as that of the phase voltage in the case of 180 degree conduction mode. So here, yes, all even and triple n, all even and triple n harmonics are absent. All even and triple n harmonics are absent. Are you getting the point? Okay, this is the phase voltage, this is the line voltage. Okay, but if you check a 180 degree conduction mode, in a 180 degree conduction mode, the nature of the phase voltage is a stepped wave. Nature of the line voltage is a Cauchy square wave. Okay, but it is a reverse in the case of 120 degree conduction mode, right? Next, now can we derive the expression for RMS value of the phase voltage? Yes, RMS voltage per phase, okay, is equal to, we can write for any waveform either VAN or VBN or VCN. Okay, so if you check for VAN, okay, whatever the waveform we are having from 0 to pi, right? Yes, exactly opposite is for pi to 2 pi. Okay, so we can take it only for 0 to pi, right? So it is like 1 by pi RMS, root means square. Okay, so it is a 1 by pi, I'm writing here 1 by pi integration from 0 to 2 pi by 3, 0 to 2 pi by 3. During this, what is the magnitude? It is a VDC by 2, right? Magnitude is equal to VDC by 2. Okay, so we can write it as a VDC by 2 bracket square into d omega t to the power 1 by 2, to the power 1 by 2, right? So from this we can write it as, yes, it is equal to VDC by yes, 2 root pi, I'm taking it outside, okay, into omega t and putting the limit, it is a 2 pi by 3 to the power 1 by 2. Okay, so it is root pi will get cancelled. Okay, this is a root 2 and here it is 2, right? So it is like a VDC by root 2 into root 3, so it is a VDC by root 6. This is the RMS voltage per phase, RMS voltage per phase. Okay, per phase RMS voltage, it is a VDC by root 6, right? Next, what about the RMS value of the line voltage? Yes, we can write line voltage, RMS line voltage, RMS line voltage. Okay, RMS value of the line voltage. So if you check, it is equal to, yes, either you can check for VAB or VBC, etc. For any value you can check. Okay, so if you check, yes, either we can take for 0 to pi or 0 to 2 pi, right? In both, for both the intervals you will be getting the same answer. Okay, so it is a VDC by 2 minus VDC by 2. Okay, so we can write it as a RMS value of line voltage. It is equal to, yes, 1 by pi. In that we can write integration from 0 to pi by 3. What is the value of 0 to pi by 3 during? It is a VDC. Okay, so it is a VDC square. Okay, plus into d omega t plus integration from pi by 3 to 2 pi by 3. What is the value? It is a VDC by 2. Okay, VDC by 2 bracket square into d omega t plus integration from 2 pi by 3 to pi. Yes, during this interval if you check, yes, it is equal to minus VDC by 2. So it is like a minus VDC by 2 bracket square into d omega t. Okay, so to the power 1 by 2. to the power 1 by 2. I am writing here. Okay, is this clear? To the power 1 by 2 I have written, right? Next, so further we can simplify it as is equal to, this can be simplified as is equal to VDC. We can take VDC by 2 outside, right? So VDC by 2 root pi, okay, into, yes, it is a pi by 3, it will be there, okay. I have taken VDC by 2 outside, okay. So it is like, or we can take directly VDC only outside, okay. So this can be written as, if we take VDC square outside, is equal to VDC by root pi, okay, into, yes, it is a 1 into d omega t, okay. So it is a pi by 3. After putting the limit, we will be getting plus VDC, we have taken VDC square outside, so it is a 1 by 2 square, so it is a 1 by 4 into, yes, if we put the limit, it is a pi by 3 plus it is again 1 by 4, and after putting the limit, it is a pi by 3 only, to the power 1 by 2, okay. So further we can write it as a VDC by root pi into, yes, pi by 3 plus pi by 12 plus pi by 12, it is a pi by 3 plus pi by 12 plus pi by 12, okay, to the power 1 by 2. So this can be written as is equal to VDC by root pi into, yes, 6 pi by 12, okay, to the power 1 by 2, right. So it is equal to, yes, 6 pi by 12, right. So this can be written as, yes, is equal to VDC by root pi into under root pi by 2, right. It is a pi by 2, the power 1 by 2, right. So it is a root pi will get cancelled, so it is like VDC by root 2, VDC by root 2. This is what RMS value of line voltage, okay, line voltage RMS value, right, RMS line voltage, okay. So this is a VDC by root 2, okay. So if you check the phase voltage, it was a VDC by root 6, line voltage is VDC by root 2, okay. If you multiply the phase voltage with root 3, you will be getting the line voltage, right. Next, what about the load power? Yes, load power, we can write the load power P0 is equal to, yes, RMS value of phase voltage, okay, phase voltage RMS value, phase voltage RMS value, where divided by R, this is the per phase power, right, into 3, because we are having the 3 phase load, so it is a 3 into per phase RMS voltage divided by R, okay. This is the P0. Is this clear? Are you getting the point? Okay, or you can find it with the under root or a root 3 VL into IL also. IL is nothing but the line voltage divided by line current. Is this clear? Okay, so this is about the 120 degree conduction mode 3 phase inverter, right, 3 phase inverter 120 degree conduction mode, okay. In the next video we are going to discuss the numericals related to 3 phase inverters. Thank you.